and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on voltaic cells. In our last lesson, we began learning about this type of cell, starting with its definition. A voltaic cell, which is a type of electrochemical cell, generates electrical energy from chemical reactions that take place within it. We also learned what a salt bridge is. A salt bridge is an inverted U-tube that connects solutions to form a complete circuit. We learned that it is filled with an electrolyte that will not interfere with the operation of the cell. Thus, a salt bridge connects the solutions in the two compartments without allowing them to mix. We also learned how to draw and label a zinc-copper voltaic cell and define cell and electrode potential. We used equations to demonstrate this. In today's lesson, we will take our knowledge of voltaic cells several steps further. We will explain how standard electrode potential is measured, and we will measure the cell potential of a zinc-copper voltaic cell using a voltmeter. We will also learn how to describe the reactivity of a metal from its position in the activity series, or the electromotive series. Let us begin our lesson. In our daily lives, we can observe water flowing from areas that are uphill, or areas of high potential energy, to areas that are downhill, or areas of low potential energy. It is very similar in a voltaic cell. Electrons flow in a wire from negative or high electrical potential energy to positive or low potential energy. As we said in our last lesson, cell potential is the difference between two electrode potentials. The potential associated with each electrode is chosen to be the potential for reduction to take place at the electrode. Thus, standard electrode potentials are figured out for reduction reactions and are denoted as E-red cell potential, or E cell is equal to E red, which represents the cathode minus the standard reduction potential of the anode reaction, E red. Since voltaic cells have half cells, we must give a standard reduction potential to a certain reference half reaction in order to determine the standard reduction potentials of the other half reactions relative to that reference. The reference half reaction is the reduction of hydrogen ion in solution to hydrogen gas under standard conditions. this is given a standard reduction potential of exactly 0.0 volts. An electrode designed to serve as a reference in measuring standard electrode potential is called a standard hydrogen electrode, or a SHE. A standard hydrogen electrode consists of a platinum wire connected to a piece of platinum foil that is covered with finely divided platinum that works as an inert surface for the reaction. Inert means that it will have no effect on the reaction. The electrode is encased in a glass tube which allows hydrogen gas to bubble over the platinum. The solution contains 1 molar hydrogen ion in solution under standard conditions. Standard reduction potentials are calculated using standard hydrogen electrodes. If the reduction potential is a large positive value, it is a strong oxidizing agent. This means that the ion is easily reduced. When the reduction potential is negative, though, it has less tendency to be reduced. Instead, it has a high tendency to be oxidized and is a reducing agent. Let us look at this cell that has a zinc anode in a zinc sulfate solution and a standard hydrogen electrode as its cathode in a solution of hydrogen chloride. In this reaction, the zinc oxidizes and the hydrogen reduces. The cell voltage, as measured by the ammeter, is 0.76 volts. Students, let us do an activity. Use the defined standard reduction potential of hydrogen ion to determine the standard reducing potential for zinc 2 plus zinc half reaction.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. If you got a standard reduction potential of negative 0.76 volts for the reduction zinc 2 plus zinc, you are correct. We can also write that like this. Students, please note that we write the reaction as a reduction even though it occurs in reverse as oxidation. Whenever we assign a potential to a half reaction, we write the reaction as a reduction. Students, please look at this chart. We can see that the reduction potential of half reactions positions them on this chart as being either strong reducing agents or strong oxidizing agents. There are two things we must remember when looking at this chart. The E-red values apply to the half-cell reactions as read in the forward or left to right direction. Also, the more positive E-red is, the greater the tendency is for the substance to be reduced. Students, let us do an activity. A Daniell cell is a voltaic cell that has a zinc anode, which we have just established the standard reduction potential of, and a copper cathode. Please figure out the half reaction at the copper cathode in a Daniell cell.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. If you got this half reaction for the copper cathode, then you are correct. If we use that half reaction, we can determine the standard reduction potential at the copper cathode. Thus, the standard reduction potential at the copper cathode is positive 0.34 volts. It is a stronger oxidizing agent because it has a greater tendency to be reduced. And the zinc anode is a weaker oxidizing agent because it is more difficult to reduce. Today, we learned how standard electrode potential is measured. We also measured the standard reduction potential and reactivity of a zinc-copper cell by looking at their half-cell reactions and the volts produced. This brings us to the end of today's lesson. Until next time, thank you, teacher. Thank you, students.